Before the advent of glowing screens and complex software, there was wood, graphite, and steel. These were the fundamental tools of creation, the instruments that brought imagination to life. The world's cars, from their initial concepts to their intricate designs, buildings reaching for the sky, and complex machines, the gears of industry, all began on a drafting table, a massive tilted wooden board, a landscape for innovation. It was here that ideas took shape, where visions were meticulously translated into tangible plans. Engineers used T-squares, sliding them across the surface with practiced ease, set squares, carefully positioned to create precise angles, and compasses for perfect lines and circles, ensuring accuracy in every detail. These tools were extensions of their minds, translating thought into form. Every line was a commitment, a decision etched onto paper. Mistakes meant hours lost, painstakingly correcting errors that could ripple through the entire design. Architects and engineers spent weeks hunched over vast sheets, their eyes scanning every detail, each line representing a real-world part, a component with a specific function and purpose. Precision was everything. The key to success, 1 millimeter off, and a steel beam might not fit, jeopardizing the entire structure. There was no undo button, no quick fix. Only careful erasing and hope you didn't tear the paper, a constant reminder of the fragility of the process. This process demanded patience, a virtue often tested, visualization, the ability to see the finished product in your mind's eye, and deep understanding of the underlying principles. Rooms filled with blueprints, stacks upon stacks, were the ultimate source of truth for builders and machinists, the guides that transformed drawings into reality. The discipline and foresight learned here in these spaces of focused creation laid the foundation for modern engineering, shaping the way we design and build today. You had to think in 3D, visualizing the object in its entirety, then translate it to 2D lines and symbols, a process of abstraction and simplification. This hands-on connection to design, the feel of the pencil on paper, is something we risk losing in the digital age, as we become more reliant on automated tools. But it taught engineers to plan every step before making a mark, to consider the consequences of each decision. The drafting table was the crucible where modern engineering was forged, a place of intense focus and creativity. It was slow, methodical, and deeply personal, a reflection of the individual's skill and dedication. Every project was a test of skill and patience, a challenge to overcome with ingenuity and precision. The lessons learned here still echo in today's digital world, reminding us of the importance of careful planning and attention to detail. The roots of every skyscraper and engine, every bridge and airplane trace back to these tables, to the hands that meticulously crafted their designs. This was where the future began, where the seeds of innovation were sown, and where the world as we know it was first imagined. Then came the computer, a monumental shift in how we approach design and engineering. It wasn't just a tool, it was a new way of thinking, massive, humming with the power of countless vacuum tubes, and deeply mysterious to those who hadn't yet grasped its potential. These machines filled entire rooms, their presence both imposing and intriguing. Early mainframes weren't designed for drawing intricate designs or visualizing complex structures. They crunched numbers with relentless efficiency, processed vast amounts of data, and even broke complex military codes during the Cold War. They were the number-crunching powerhouses of their time. But curiosity, as it always does, sparked innovation and pushed the boundaries of what these machines could do. Engineers and scientists began to wonder, could these computers be used for more than just calculations? Ivan Sutherland's groundbreaking Sketchpad in 1963 allowed people to interact with the digital world in a completely new way, letting them draw directly on a screen with a revolutionary device called a light pen. This was more than just drawing. This was the birth of computer-aided design, CAD, a concept that would forever change the landscape of engineering and architecture. Suddenly, instead of painstakingly redrawing entire blueprints, you could move a car door handle on a screen with a few simple commands, making adjustments and refinements without having to redraw everything from scratch. The promise, the tantalizing vision, was speed, unparalleled efficiency in the design process, and freedom from the tedious, repetitive task of redrawing everything by hand. Early CAD systems were undeniably expensive and incredibly complex, making them primarily reserved for the giants in industries like aerospace, where precision and innovation were paramount, and automotive, where the ability to quickly iterate on designs could lead to significant competitive advantages. The software itself was often slow and clunky by today's standards, screens flickered with an almost hypnotic rhythm, and the learning curve was steep, making it tough for many to adopt. Many engineers, comfortable with their familiar tools and techniques, clung to their pencils and drafting tables, skeptical of these newfangled machines. But the core idea, the potential, took root and began to spread. The realization that computers could not just calculate, but also visualize complex designs in ways never before imagined. This was a fundamental paradigm shift, a change in the very way engineers and designers approached their work. It was a merging of traditional drafting precision with the immense computational power of the digital age. The digital age of design, though in its infancy, had officially begun. Engineers started to see the potential for creativity and innovation, not just rote calculation and drafting. The transition from paper to pixel was slow, fraught with challenges, but ultimately inevitable. The seed of digital design had been planted, and it would soon blossom into a revolution. The traditional drafting table and the cutting-edge computer terminal began to share the same workspace, a symbol of the changing times. The future of engineering was rapidly changing, driven by the relentless march of technology. The first tentative step toward the creation of digital blueprints, accessible and modifiable with ease, had been taken. The world of design, forever bound to the constraints of paper and ink, would never be the same again. The revolution had started, quietly at first, but with an unstoppable momentum. The age of CAD was officially here, ushering in a new era of innovation and efficiency. As computers shrank in size and grew in power, a monumental shift began to take place in the world of design and engineering. The bulky mainframes that once dominated entire rooms were slowly giving way to more compact and accessible machines. CAD software, once confined to the realms of elite research labs and specialized institutions, started its journey into the mainstream. The promise of digital design was no longer a distant dream, but a tangible possibility. Then came AutoCAD, released in 1982, a watershed moment that would forever alter the landscape of engineering and design. It was a game changer, a disruptive force that democratized access to powerful design tools. AutoCAD brought digital drafting directly to every engineer's desk, transforming the way they worked and thought about design. The era of manual drafting was drawing to a close, replaced by the precision and efficiency of the digital world. No more million-dollar mainframes tied to specialized rooms and dedicated staff, just a PC sitting on a desk and powerful software capable of feats previously unimaginable. The barrier to entry had been shattered. Two-dimensional CAD effectively put the traditional drafting table right on the computer screen, but with superpowers that no physical drafting table could ever hope to match. It was a quantum leap in design capabilities. Now, you could draw perfect lines and circles with a simple click of a mouse. No more need for a T-square or compass, or the painstaking precision they demanded. The digital tools were far more forgiving and efficient. The introduction of layers allowed you to separate electrical components, plumbing systems, and structural drawings into distinct, manageable elements, a feat that was virtually impossible to achieve with traditional methods on paper. Editing became instantaneous. Imagine being able to change every bolt diameter in an assembly with a single command. The level of accuracy soared to new heights, and the potential for human error plummeted, leading to more reliable and consistent designs. Designs could be updated and revised with ease, and then sent to manufacturing facilities in mere moments, streamlining the entire production process. These digital files could then be fed directly into CNC machines, creating a seamless link between the initial design and the final production of the product. The result: better products built faster with significantly fewer mistakes and a higher degree of precision. Suddenly, small firms could compete on a level playing field with even the largest industry giants. The digital blueprint was officially born, revolutionizing the world of manufacturing and ushering in a new era of industrial transformation. The entire process became cleaner, reducing waste and promoting a more sustainable approach. It was faster, more efficient, and far more organized than anything that had come before. The foundation for the next great leap in design and engineering was firmly set in place. The world of engineering was truly democratized, opening up opportunities for innovation and creativity on a global scale. The era of the digital blueprint had officially arrived, transforming industries and reshaping the future of design. And with 2D CAD firmly established, the stage was now set for the next revolution, the advent of 3D design. The world isn't flat, so why should our designs be? 2D CAD required engineers to imagine 3D objects from flat drawings, a risky mental leap. Enter 3D CAD software like CADIA and SolidWorks. Let you build virtual objects, not just draw them. Sketch a profile, extrude it, cut holes, round edges, now you're sculpting, not just drafting. Rotate, slice, and inspect your model from any angle. Instantly see if parts fit or clash, no more guesswork. Prototyping costs dropped, and creativity soared. Complex, organic shapes became possible, think of a car's aerodynamic curves. 3D modeling unlocked new levels of innovation and efficiency. Engineers could now design, test, and refine in a virtual world. The leap to 3D changed everything. 3D was huge, but parametric modeling was the real game changer. Now designs had intelligence. Change one parameter, and the whole model updates. Imagine a bookshelf. Adjust the height, and every shelf resizes automatically. Assemblies took this further, combine parts, define how they fit, and the software enforces real-world constraints. It's like Legos that know how to connect. Jet engines with thousands of parts are built and tested virtually first. Change a single blade and the whole engine adapts. Errors are caught before anything is built. This digital flexibility enables rapid innovation. Complex machines are perfected in the virtual world. Parametric design means faster changes, fewer mistakes, and smarter products. The digital prototype is now the heart of engineering. The future is adaptable by design. With a perfect 3D model, it's time to test virtually. Finite element analysis, FEA, lets you stress test parts on your computer. Apply forces, heat, or motion. See where your design bends or breaks. Color-coded maps reveal weak points instantly. No more expensive, time-consuming physical prototypes for every change. Simulate airflow, heat dissipation, or suspension movement with a click. Optimize by removing material where it's not needed, lighter, stronger, better. Digital testing means faster iteration and smarter designs. Engineers can innovate at the speed of thought. The virtual lab is open 24/7. The best ideas survive before a single part is made. Collaboration used to be slow files sent back and forth, versions lost. Cloud-based CAD changed everything. Now, teams worldwide work on the same model in real time. Changes are instant, conflicts flagged, and everyone stays in sync. Managers, clients, and suppliers can view and comment from anywhere. The global workshop is always open. Innovation moves at the speed of the internet. Engineering is now a truly connected conversation. The frontier now is blending digital and physical worlds. VR lets engineers step inside their designs, walk around, and collaborate virtually. AR overlays instructions and data onto real objects, repairing and building with digital guidance. Generative design flips the script. Tell the computer your goals and AI invents thousands of solutions. The results are organic, efficient, and often surprising. Engineers become directors, guiding AI to the best answers. Human creativity and machine intelligence combine for supercharged innovation. These tools aren't science fiction, they're here now. The future of design is immersive, intelligent, and collaborative. The next leap is already underway. From pencil to pixels, every tool has unlocked new possibilities. The drafting table taught discipline. CAD brought speed and precision. 3D modeling made ideas real. Simulation and the cloud connected and accelerated us. Today's tools are more powerful than ever, available to anyone, anywhere. VR, AI, and generative design are just the beginning. The real power lies in your hands. What will you build? What problems will you solve? Push the limits, break the software, and invent what comes next. The future of engineering is yours to shape. The digital forge is lit, waiting for your ideas. The world is full of challenges and opportunities. Go build something amazing. The next chapter starts with you.